Good afternoon, and a very warm welcome to our afternoon panel session on defending the cyber front with AI. My name is Bruce Watson, and I have the pleasure and honor of hosting this session this afternoon. I happen to be a researcher and also a practitioner in both cybersecurity and artificial intelligence, and it's my pleasure to bring to you a couple of very interesting speakers this afternoon. Of course, we'd like to start off just by thanking CCDCOE for their organization of such a top-shelf conference. It's really outstanding work. So it's a real pleasure, as I said, and an honor to have you with us today. We know that you had a couple of choices of different sessions that you could have attended, and it's very nice that you've chosen to join us for this one in particular. If I look at the topic area of artificial intelligence combined with cybersecurity, it's a very exciting and highly relevant part of the current cybersecurity threat landscape. And there are two subtopics in particular that we'll be talking about today that really mesh with, I think, the most advanced topics that occur within both of these fields. The first of them is explainable AI. So typical artificial intelligence systems involve constructing a system, often built from a lot of data. These are so-called training data that are then used to build an artificial intelligence model. Most typically, this is using machine learning algorithms. And as a result, we have an artificially intelligent system, which may be very narrowly focused to the particular domain, but is able to solve particular problems within that domain, but it doesn't shed any light on the internal structure of that domain. So in other words, the solution is a black box solution, and we don't really have any deeper understanding of the structure of the cybersecurity threats. So it eventually becomes important to be able to gain that deeper understanding and to really be able to understand why the system is making the certain decisions that it does. And this would lead us to wanting a kind of system that's a so-called glass box system or an openly explainable AI system. Now, it turns out that such systems are exactly the holy grail of the artificial intelligence research. So as desirable as they are, it's an extremely difficult technical problem to solve, and a vast number of researchers are working on this worldwide. So we'll have the pleasure of talking a little bit about one of those in the particular subdomain today, which is very important progress. The other one, of course, is, as mentioned, autonomous systems. So along with explainable AI, we would also like to be able to have autonomous artificially intelligent systems. And I'm not talking here about offensive systems, but autonomous defensive systems that can take care of certain aspects of cybersecurity all on their own without human intervention. And this is then something that, of course, provokes a large amount of international debate. It has an ethics component to it as well, which is something that makes the news very, very quickly. And so it's a pleasure today to also hear from one of the speakers about recent work in towards autonomy of such cyber defensive systems. So that, coupled with explainable AI, will be the two axes of the research that we discuss today. So let me get to the two speakers. These are two speakers that you probably will recognize from previous years. The first one is Artur Zlafranov, and the second one is Roland Mayer. And you can, of course, read about their biographies within the proceedings and on the website of CyCon 2021. But in a nutshell, Artur is a researcher at NATO CCDCOE. He's got a strong interest in web and network technologies. He's been working on, of course, cyber exercises, lock shields in particular. And he spent some time also teaching at the University of Latvia, which happens to be where he is currently a PhD candidate working on his dissertation. Our second speaker today, I also have the pleasure of introducing, is then Roland Mayer, and we'll be getting to him as our second speaker. Roland is also involved as a PhD candidate, in this particular case in electronic engineering and information technology at ETH in Zurich. And his interests are in security of computer networks, of course, like many of us as well. But he has a particular interest in being able to use and leverage recent advances in software-defined networking and programmability of networking. And he happens to have obtained his master's degree at ETH Zurich in the same department as well. So he's very much at home in this kind of research. So let me get to the format of today's talk, because I think you're not here to necessarily hear me talk, but rather hear the two viewpoints of our speakers, and we'll be able to return to a discussion afterwards as well. So we're going to be starting off with Artur in just a moment before going on to Roland. And I would very much like you to already, as we proceed, to think about particular questions you may have. It allows the questions, if you pose them soon enough, to filter through to us and to order the questions so that we either discuss some of them in between the two talks, or so that we could return to them in the larger discussion at the end. Now, in the event, of course, that you're watching this after the fact in the archived version of this session, please feel free to email us. We're very happy to engage on this topic after the fact as well. So without me taking up more of our time, let me please turn it over to Artur, who's going to be discussing explainable AI in a particular problem subdomain. Thank you. Please begin, Artur.
Thank you for introduction. And today we are going to discuss one very, let's say, specific topic. And the specific topic is classifying devices on the internet. And we will go into detail why it's important later on, but currently we are trying to combine expert knowledge and, let's say, research knowledge. And my co-author is Dr. Roman Graf. He has been in CyCon for many years. And when we started a few years ago this research, he was a full-time AI researcher in Austrian Institute of Technology. And now he is transferring his knowledge to private sector into Accenture. So what is the problem? So the problem, we have a lot of devices on the internet. In reality, there are billions upon billions. And predictions say that in a few years, we would talk about 10 billion or 20 billion of devices. So what kind of devices are these? So we are particularly interested into reachable devices. What does the reachable means? Means it's listening on one or more ports, and this traffic is directly routed to this device instead of being dropped somewhere. So anyone can send a packet on particular port to this device, and this device will process it. If anyone can send something, anyone can send malicious payload. Maybe this device is vulnerable, maybe not. If it's not vulnerable, it might become vulnerable in 3 years when it's still connected in the same way. So this is kind of a huge problem. And there are a few causes for it. First and foremost, manufacturers. We see even today manufacturers selling devices, selling cheap devices for 10, 20, 30 euros that does some function in your home, some IoT devices, and they have insecure default configuration. And some states are trying to battle it with some regulation, but we are far from solution. An insecure default configuration would mean the stuff that should be listening only internally is listening to the internet. So this is the easiest way. We have seen through our research a lot of vendors, a lot of solution vendors that buy devices in bulk and develop solution from them and deploy in homes or in commercial organizations, and they have some remote administration or remote services that this vendor can support it. And if it turns out there's vulnerability, then anyone can compromise these devices, and maybe all devices by a specific vendor. And users, of course, users often plug something in a way it shouldn't be plugged. They click some settings that shouldn't be clicked, and they expose themselves to the internet. And this is extremely common. Or maybe there is solution to vulnerable or reachable stuff, and user just does not update software. And we should look into mirror and ask ourselves, when was the last time we updated software to our routers or our IoT devices or something? And the answer usually is never. And what is the result? Result, from many billions, there are hundreds of millions of reachable devices on one or more protocols. And in reality, maybe few millions are actually needed. few millions which provide function on a network or on the internet to the public, and that's all. Or we need some kind of direct access without cloud intermediary. That is also a valid use case. But do we really want our network router to be compromised if we are end user? And if our network router is compromised, it's bad. It means that any malicious actor can do anything to us, steal our data, inject some data, inject malware. So a lot of bad things happen because everything flows through network routers. And individual devices or set of devices, it does not even need to be individual, affects the whole regions. I mean, we saw just recently fuel shortage because of hacker attack. It does not necessarily mean that this was the cause, but we can expect that anything that is exposed to the internet might be compromisable. We might lose power, we might lose water, we might lose fuel. So there are no good scenarios for that case. And besides being compromised, of course, there are other risks. Risks that there are reflector software running that could be sending traffic to some victims and contribute to the problem. Or maybe there is some proxy service running and fraudsters use it to conceal identity and use clean IP address. So many options. So what is the current state or state few years ago or even a decade or two ago? So classification of devices is very old topic. It's after internet appeared with consumers and commercial organizations, the classification is under let's say research topics. And we might know Shodan, we might know Census. These are huge indexes of all devices on different protocols. And you can click a category there, and what will happen? Will happen that there are limited set of static rules, usually few thousand, maybe 10,000. And according to these rules, the devices are kind of split around. And the issue with that is that heterogeneity of devices increases. So there are more and more devices from more manufacturers. Every day there are more different ones. And it is not feasible to write manually a lot of rules. It's extremely complicated. And it operates on a data that is usually referred as banner grabbing. And what it means, it just means sending a packet or two and receiving the answer with some kind of welcome message or some kind of debugging message. So and parse and process that. And it is perfect. If the rules match, it's perfect. It's fastest, most efficient classification way. Except if no rule matches properly, then we can't classify device at all. And because of the variance of the devices increasing, it's a huge problem. And manual classification, which is also quite common if we have individual device. It might take 1 minute, or it might take an hour, or it might take few days. But if there is some way for it to be classified, usually with active probing and enumeration and stuff like that, an expert can achieve high accuracy, but I mean only for a few individual devices. So, as Bruce mentioned, this is holy grail of application in the cybersecurity domain, because cyber expertise is common. You can't take a person from the university and he will instantly become an expert. It takes years. It takes a lot of financial resources so to train an expert and keep him without leaving. So this is a huge problem, and these experts are in high demand. And what we want to replicate. Ideally, we want to replicate experts' knowledge. And this is very, let's say, far away goal. We can't really do it right now. But what we can do, we can start replicating some of the expertise, some topic where there is knowledge, where there is intuition. We can work with experts to define this and train some machine learning classifiers to work on this. And even some adoption would decrease expenses and increase overall security. So AI for device classification is not this year's topic. This topic is 3-4 years old when different teams around the world started working on it. And there are two directions. It's either reachable devices, meaning the ones we discussed, or there are traffic flows, means you need some special privileges to observe in a specific network point the traffic and classify it passively. And what is our goal? Our goal is to close the gap between static classification, static rules, and expert classification. And what we want to do, we want to classify large sets with expert accuracy. This hasn't been done ever, and until a few years ago. And you want to classify individual devices instantaneously. Now, if you want to classify individual devices, you need an expert. You need many hours, possibly. And here, we could do it cheaply and quickly. So a year ago in CyCon, we presented our own research from this field, and we used artificial neural network. We selected features, we explained classes, we explained statistics. So if you are interested in this topic, this is introductory paper for it. And now we build on top of it. So the challenges are extremely similar to anything in AI research. It's labeling training set. And in this specific case, the rules become conflicting. The more you create rules, the more conflicts you find. And it means they become more complex and more longer and slower. So you can't reasonably classify by defining few thousand rules manually. It's just after that few thousand, it becomes one device or a few hundred devices, but we are talking about sets of hundreds of millions. You can't really match everything. And there are automation approaches which are great, and there are research that produced hundreds of thousands of rules, but they produced it in a way that every rule needs to be manually verified to trust them, and they did not have resources. We don't have resources to expertly analyze hundreds of thousands of rules. So what is next? It's accuracy, because it is easy to show high accuracy, and it is somehow easy to achieve high accuracy. And the question then becomes, if you have high accuracy, is it really high accuracy? And this is kind of problem of misclassification. If we if we look at the problem, artificial neural networks are black boxes, so we can't really figure out what is happening. And what is the solution? Solution is what is challenges? Challenges are that every research in this topic claims accuracy between 80 to 97%, which is great. But if you start randomly sampling and provide this to expert, he might question it, and that is the problem with every research currently available. So the great example that has been publicized is there are ICS devices, many ICS devices in many data centers. So why? And it's easy to answer from an expert position. Expert says either it's honeypots or there are some ICS devices needed for supporting data center. It's and some other versions, but it sounds easy. But why did it misclassify? Because it's not trained properly. Maybe we need to add extra features like data centers, data center identification. Maybe the labeling rules or label creation was poor quality, because it's a huge manual labor, and let's say experts or top level scientists don't have time to deal with it. Maybe features were poorly extracted. So there are a lot of questions. And what is the solution? Okay. So first, we do not know what is the problem, because as we discussed, it's a black box. We don't know what's happening. And if we don't know what's happening, we can't really fix anything. So what's the problem with misclassification? So in research, it is okay to have bad results. In science, same. So we always want the best, but we will take anything. And if we can provide next year or a few years later better results, better accuracy, this is perfectly fine. This is research. If you look at let's say industry or cyber defense, trustworthiness is a huge problem. And I'm ignoring adversaries. I'm just talking about current state. Let's take one scenario. There is data flow. This data flow is malicious. It's encrypted, so we don't really know what's happening, and it's fine to have encrypted traffic. The classifier misclassifies it, and 97% seems good. Well, we have 100 flows or 30 flows and one malicious flow. So this malicious flow, let's say, goes through the accuracy. And of course, you need defined policy. And this policy states that, let's say, it's okay to have encrypted traffic to web, but it's not okay to have encrypted traffic to other places. And we misclassified, our data got exfiltrated. So false negative of not blocking single instance is catastrophic. It's a complex solution, and we are kind of in a problematic state. So, and false positive, well, there is some usability issue, but it's perfectly fine. So how can we solve it? So solution is explainable AI. And it's by, let's say, workflow and development, it's the same as almost all other machine learning classifiers. So what is different? That we use naive Bayes class model, and we use Lime framework for explanation. So otherwise, it looks the same as many other workflows for research. So let's look at some examples. What is our current state? Some random devices. So what does explainable AI really provides it? It provides us different weights for classes. So highest weight is chosen for classification outcome, and it provides us weights for features. And weights could be positive, could be negative. So what would this explanation mean? For this device, it would be that it's a SPA device, which is quite common for likely Cisco or something that we train. So this is for every specific device we have different weights. So the same, let's say, features might have different weights for different devices in the same class. So this is kind of normal. And so let's look at the printer. What the printer says that it's HP. We all know HP. We know OfficeJet. So this is perfectly fine. And what's interesting is that there are, let's say, some keywords and some features from many different places, including autonomous systems. So the finance feature is from network names. So financial institutions have more, let's say, printers than other ones. IoT device. So interestingly, for IoT device, security headers are kind of negatively weighted. So IoT device by our model have much less security features. And if there are security features, it's less likely to be an IoT device. Interestingly, there are specific devices in Austria. So country code or network name is weighted for this specific device, which is actually located in Austria, positively. So infrastructure devices, meaning controlling some kind of network or some other non-ICS features. And here we have a VMware Horizon device, and it's quite easily classified by a static rule. So nothing, let's say, surprising here. For ICS device, it is extremely interesting. As we see here are so little features. So many features were, let's say, filtered out by us as a noise, and what is left is extremely limited, only four features. And the analyzer, it's a spectrum analyzer, but spectrum is also, let's say, a network name for in USA, so it is weighted negatively in this case because it's a consumer network with not really many ICS devices. So network devices. So what do we see? We see that if it's in gateway, then it's likely a network device, while there are possibly other type of network devices. And we have specific incorrect, let's say, incorrect login or incorrect name for a huge number of devices, and for this case, it is weighted as heavy feature. For IP cameras, we have Hikvision. It is only software that is DNRS webs. It's only software that is used in Hikvision, and no other device classes uses it. So it's obviously the highest weighted feature, and it would be classified same way by an expert. For web server, it's quite clear that if we have Apache, it's likely a normal web server. If we have some kind of documentation description, it's a default installation without virtual hostname. So this is kind of normal. And unclear, these unclear and uncategorized devices, these are devices that are extremely hard to explain, because what we see, the features are very generic and nothing is, let's say, weighted in a highly positive way that could be classified by an expert even. So overall, what we see is that over the 3 years, surprisingly, ICS devices are in increasing numbers. These are low impact devices, but still they're ICS. We have infrastructure decrease. IoT is stable, which is great because number of IoT devices increase, but the percentage stays the same. Network devices are in decrease, so this is great because network devices are the ones that everyone has in their homes where the internet cable connects to. And IP cameras are stable, in decrease, so there are more cloud cameras available. So future works is just to move on and analyze misclassifications, because now we are transferring our knowledge between model and expert. So now experts are learning how the AI thinks. Next step is to transfer the knowledge back to AI, and then we will see how can we improve it. Okay, thank you.
So thanks very much, Artur. I really appreciate that talk, and I'm sure the audience does as well. I don't see immediately that there are questions we should deal with at this moment, and so we'll move on because I think you've given us enough food for thought for the discussion at the end. And I'd like to start off then immediately with Roland, if we may. And Roland is going to be talking about an AI-powered game player for cyber defense exercises. And it's worth noting that Artur is actually also a co-author on that paper. So we can clearly see there's a lot of crossover research that gets involved here. So Roland, if we may switch to you. Thank you.
Thank you. And I'm happy to present our work on this AI-powered cyber defense player. This is, as you already mentioned, it's a joint work with Artur as well as Kimmo Heinare from CCDCOE and Luca Gambazzi and Vincent Lenders from Arma Suisse. To start, let's imagine your job is to mitigate 2,500 attacks against about 4,000 systems that you're managing. So this sounds like quite a stressful job, but in the end, it's basically what the blue team members at LogShields need to do every year. LogShields, this is the world's largest cyber defense exercises, takes place every year in Tallinn, and it is a so-called red team versus blue team exercise. This means that there is a red team, which consists of the attackers, and there are many blue teams, which are the defenders. And usually there is one blue team for each participating country. We started to look at this exercise from a research perspective some years ago already. And maybe some of you remember 2 years ago, I was presenting a paper describing a system where the collaborators and we developed a system that could identify command and control channels in the environment of this LogShields exercise. And we have shown that actually a fairly simple classifier is enough to detect large parts of the command and control channels. And we also confirmed with the Swiss team, which was participating at this exercise, that this system actually works in practice and it was beneficial to them. For this year, the colleagues that I mentioned at the beginning and we were thinking about going one step further. And this time, we don't just want to provide some automated tools that the blue team can use to have some more automation inside the team, but we want to have a fully automated blue team. So that's a blue team where there is no human labor required anymore. Instead, everything is fully automated. And the question that we answer in our paper and in this presentation is, what will it take to have such a fully automated blue team? In the presentation, in the paper, I will present you the architecture that we envision how such an automated blue team could be implemented and the components of which it is consisting. I will not be able to present you a full implementation or results. This is not in the scope of this paper, but we hope to inspire other people, and we ourselves, we will be working on this more in the future and hopefully end up with such an automated team in a couple of years in a future iteration of blockchains. So when we want to automate a blue team, what would it mean actually? For this, let's first look at the tasks that such a blue team would need to perform. First, at the very high level, the task of a blue team is to defend its network. So the network, usually spoken of as the game net, is consisting of many different types of devices. This can be different workstations with different operating systems, with different versions, servers providing different services, but also IoT devices and ICS devices and some other special devices, including things like drones. And the blue team then needs to defend this network against attacks. It does so in usually three main steps. First, it needs to perform initial hardening, which means to get familiar with the environment, with the network, and do some configuration changes such that the systems are more robust against attacks. Then when the attack starts, the main task is mitigating these attacks and restoring systems that have been compromised. And at the same time, the blue team also needs to communicate with other teams over predefined channels. Now, this communication is maybe not so hard for a human team. If we are speaking about a fully automated team, this will be more involved, of course. And communication here means essentially maintaining 4 different communication channels. The first and probably most important one is with the so-called user simulation team. This is a team consisting of people that simulate real users. So these are people that would access websites that are hosted in the GameNet or send emails over the GameNet and so on. And if something is not working as expected, they send a support ticket to the blue team telling them, hey, this is not working, please fix it. Then there is a yellow team to which a blue team needs to provide periodic reports about the current status of the network and successful and failed attacks. There is a white team that uses voice and video calls through the GameNet, and there is the green team providing information about the current status from a scoring perspective, and it provides services such as the reverting of devices to the initial state. The exercise itself can be seen as happening with 4 different stages. The first one that I already mentioned, this is what is called initial hardening. Here, the blue team typically prepares the system such that they are robust against the attacks which are starting afterwards. Then there is the monitoring and response phase in which the red team starts attacking and the blue team needs to respond by blocking the attacks or recovering systems that are compromised. At the same time, the blue team also needs to do this reporting that I mentioned to other teams, for example, the support tickets or the reports about the status of the game network. And also, if nothing else helps, there is a recovery stage where the system can restore compromised systems. Either the blue team can restore compromised systems either from its own backups or from the initial state that was provided from the exercise organization. Now, looking at the framework that we developed at the very high level, it looks quite straightforward. We have 3 components. One is input, the other one is control, and the third one is output. Looking at it a bit more closely, the input is what we call sensors. And these are basically components that provide data wherever one can collect data. This can be network traffic, it can be event logs, monitoring information, support tickets, or the credentials to access all the devices. On the other side, we have the output, which we call actuators, and these are components that allow to perform some actions in the exercise environment. It can be the remote management of devices, it can be changing firewall rules, resetting devices, sending chat messages, and writing the reports towards the other teams. In the middle, we have more of the intelligence, consisting first of a situational awareness database, which contains all the information that we have somewhere. an AI engine, which trains machine learning models, for example, and a control logic, which connects the information that is there with the actions that should be taken. And in the remaining of the presentation, I will now go in more detail into all of these building blocks. And in the end, I will show a little case study with a concrete example of a problem that might occur and how this automated team could handle it. So let's look at the sensors first. Sensors can be placed at 5 different positions. First, we consider organizational inputs, everything that is provided from the exercise organization. So this is, for example, the topology of the network or the device credentials. Then we have network sensors, which provide information about the network. Device sensors providing information about all the devices connected to the network. Application level sensors, which provide information about running applications. And finally, user interaction sensors, which receive all the information provided by the users of the system. So I will provide a few examples now for each of these types of sensors. Organizational inputs, these are, as I mentioned, things like the system documentation, the devices and the services that are running in the GameNet and that should be kept running. It includes the credentials to access and configure all these devices. It includes information about the scoring rules that basically define the blue team what it should do in order to perform well. And it includes information about the external monitoring, which is essentially the current performance that the blue team is achieving and the current scores that it gets. Second, we have the application sensors, which receive information about each running application, such as, for example, for a database application, it can be the users and their permissions, what they can do in the application. And it also can receive information about the application state, such as the update status and all kinds of log files. Similar for the device sensors, which report device-wide information, such as the operating system that is running, device-wide logs, such as the people who were trying to log into the system. And it can include additional monitoring systems, such as screen capture or basically whatever the blue team wants to deploy. Then next, we have the network sensors, which on one hand provide information about the network configuration and the state. This includes things like firewall rules, the topology of the network, the loads that the network is currently experiencing and whether all the links are up. But most importantly, it also allows access to all the traffic that is exchanged in the network. And this traffic can be captured and further analyzed in other systems, for example, to detect malicious connections there. Finally, the user interaction sensors, these are mostly about interacting with the user simulation team and the support tickets that it creates. So we move on to the next building block of our framework. This is what we call the actuators. And similar to the sensors, we group them into 4 categories: for network level, device level, application level, and the user interaction actuators. Again, I will provide a few examples. For application level actuators, we see, for example, application firewalls that could be deployed, such as the web application firewall that inspects all the requests to a website. Such application actuators can change the configuration of an application, for example, which user can perform which actions inside a database application, for example. And such an actuator can also install patches to fix known vulnerabilities to the application. On the device level, we see the main purpose of an device level actuators in doing remote management, ideally over multiple channels, such that if one of the management channels is compromised from the red team, there is still a way to access all the devices. And another purpose of device level actuators would be to restore a previous state of a device, either the state that it had before the exercise started or from a backup that the blue team created beforehand. The network level actuators, these are mostly about changing the network configuration. And I think the most important part there would be to change firewall rules that define what kind of traffic is allowed to go through the network at which point. The user interaction actuators then would provide information to the users, for example, through chat and email messages, which respond to the support tickets that we mentioned. And they could generate the incident reports about successful or failed attacks and also provide them to the green team. So that brings us already to the next component, which is the situational awareness database. Here it's fairly simple. This is just a collection of all the information that we have somewhere. It's all the data that we receive from the sensors, all the AI models that we train, and which I will go into details in a second, all the outputs that we send to the actuators, and also external information such as known software vulnerabilities or signatures of known malware, for example. Speaking about the AI engine, here we distinguish between 4 levels of AI that could be there. The most basic level is what we call reactive narrow AI, and this is just simple. These are just simple signature-based decisions. So taking a signature of a file and comparing it to a list of known malware signatures, for example. Level 1 is called limited memory narrow AI, and this is typically what is meant with machine learning today. So this is taking a data set, extracting some models from it, and applying these models to potentially other data sets in a supervised or unsupervised or semi-supervised way. More sophisticated would be level 2, which is at the same level as human intelligence, or even more sophisticated level 3, which surpasses human intelligence. But of course, these 2 upper levels, they don't really exist today, and if they would exist, we probably would not need to define this architecture because the AI would already do it for us. So we focus in the paper and also in this presentation on level 0 and level 1. For these types of AI that one could do, we identify 5 different tasks that for which it could be used. First, it could be used for identification and classification, which answers the question of what is it a certain object. So, for example, if the object is a support ticket, the identification could say it's a support ticket complaining about email is not working. Then categorization would answer the question what belongs together. If there are many support tickets complaining about the same problem, it could determine that all these support tickets complaining about problems with the mail server. Assessment would tell whether it's important, so whether the blue team should care about these problems with the mail server. Recommendation would recommend something to be done, for example, restart the mail server. And prediction would answer the question, what will happen if we perform this action? For example, what would be the impact on our scoring if we restart the email server? And I will now provide more examples for these AI tasks in all the 4 stages of the exercise. I will only mention some individual examples here. If you want to have the full table with all the tasks, all the phases, and many more examples, please have a look at the paper. In the initial hardening phase, for example, a categorization problem could be to find groups of similar devices that should be treated in a similar way afterwards. In the monitoring and response phase, a classification problem would be to detect malicious network traffic. This is basically what we did in this paper 2 years ago, where we classified between benign and malicious command and control network traffic. Or a categorization problem here would be to detect malicious patterns in log files. In the reporting phase, it's all about providing human-readable reports. So the categorization here could group support tickets together with monitoring alerts. So people complaining about email is not working, and the monitoring alert saying that the mail server is down. A categorization system could determine that these 2 types of information are belonging together. Then in the assessment, an assessment problem would be to prioritize the most important support ticket. Recommendation to formulate a response to them, and prediction, again, for example, the impact that this response has on the scoring. In the recovery stage, then, classification problem would be to find devices that need to be recovered because they are compromised. And the categorization problem would be to find similar devices that might act as a template for recovery. So if, for example, on one Windows device, a file is corrupted, then maybe one can take the same file from another machine and use this as a template for recovering the file on the corrupted machine. So that's about AI. The last block is the control logic, which connects all the information that we have with the actions that the blue team would take. Again, we're looking at the 4 phases of the exercise here. First, in the initial hardening, the control logic would probably determine to deploy additional software, such as application firewalls, antivirus software, or additional monitoring agents. And it could install some patches such that all software is up to date. And it could change all the passwords to have a secure initial configuration of all the devices. In the monitoring and response phase, it would disable exploited services when a model, for example, says that the service is most likely exploited, then the control logic could disable it. It would monitor and block malicious system calls, and the same monitor and block malicious network traffic on the 2 different levels. For reporting, it would generate the human-readable reports either periodically for the green team, or when there is a request, a support ticket from the user simulation team. Finally, in the recovery phase, the control logic could try to do self-recovery if there is a backup from previously, or it can revert the devices to the initial state over the exercise organization, and which would result also in a penalty in the scoring. So that's basically all for the components of this framework. In the last part, I would like to show a small case study which connects all the things that we've seen before with one concrete example. And the example here is that a user receives a link, clicks on this link, downloads a malicious file, and executes this file. And this is, by the way, something that this user simulation team would do, and could be a problem for the blue team, of course. So what can we do against this, or what could the automated blue team do against this in the initial hardening phase? First, it might configure all the clients to send HTTP traffic via a proxy, such that this proxy can inspect the traffic. Second, it could enable detailed logging about files that are opened or executed on a device. And third, it could set up the recording of all network traffic and extract meaningful features from it. Then when the attack happens, or the user downloads the file, there are the 3 levels at which this attack or the potential attack could be detected. First, the proxy can detect that there is a malicious payload that the user tries to download. Second, the logging could report that a user tries to execute a potentially malicious file. And third, the network sniffer would detect that a device is trying to establish a connection to a command and control server. And in all of these 3 states, the system could react accordingly. It could remove the malicious payload, block the execution of the file, or drop the traffic towards the command and control server. For reporting, the system can take the information that it has, the IP address from the web server where the file was downloaded, maybe the name of the user, the type of the malware, the IP address of the command and control server that was it was trying to connect, and so on, and compile all of this into a human-readable report. If the detection of the malware was not successful, then the automated blue team could restore a device to a state before the malware was downloaded. So with this, I'm coming to the end of the presentation. What I presented you today is this framework that we think would enable an automated blue team in some future iteration of log shields. What I didn't present is an implementation of this or results. This is because these parts are future work, and we don't think that it will be easy, but we definitely think it would be interesting to compare the performance of such an automated team with the highly professional blue team members in the normal human teams. So hopefully this presentation also inspired some people to work on that as well. For example, also merging existing work, which there is many, into this framework and implementing the missing pieces and the links between all the components. Of course, the same framework could be adapted for other exercises, and it could even be adapted to real-world cyber defense, even though I think there the work that will need to be done is much, much higher than to just try it in an exercise environment. So with this, I'm at the end of the presentation. Thank you all for your attention, and if there are questions, I'm happy to take them.
So Roland, thanks very much. You really shed a lot of light on what I think is one of the core issues that we all face within cyber defense. And of course, Artur, as you know, you shed a lot of light on some of the other details, which are very much a pleasure to hear about. So before I even get to some of the other questions that we can formulate, I have questions already coming in. And this one is directed to you, Artur. If you can please provide more details on how the data sets were collected. In particular, because so many new devices are connected to the internet, how feasible is it to develop a machine learning classification model that can actually be used in real life? So I think this is then the core question that we often see from machine learning. Would you like to comment on that, Artur?
Yeah. This is a great question, and I maybe did not have enough time to explain it in detail. So I mentioned that, like, variance or heterogeneity of devices increase, and this has been happening all the time, but now it's happening exponentially. Like, anyone can make a device, and anyone can redefine some properties. So from let's say some kind of static rules, they seem completely new device. And this is actually the reason for this and previous research, that this amount of increasing devices actually hurts static rules much more. So static rules can't make a good guess for the new devices. What we see is that like our models that we are using for 3 years, we are kind of we are getting some results, some guesses, and these guesses are quite good in the time. But the issue is that, of course, we need to retrain the model every year, every half year. So this is a problem. We need an experts to classify training sets, and it is kind of time consuming and expensive. And was there any other part for the question?
No, I think actually you touch on a very important question, if I can take it in a different direction then, Artur. Thanks very much for that, because you connect with the issue of having a human in the loop. And this is, of course, very important for retraining models periodically and for monitoring models as well. So I would like to, in the time remaining, maybe just make one research statement, and we can see if this research statement resonates with you. We'll go first to Roland in a moment. But the statement is that AI engines really are the only feasible way for cyber defenders to keep up with cyber attacks and cyber attackers. Just the pace of development and a kind of entropy argument that it's easier to break things than to fix and defend things. Furthermore, I would say that explainable AI is perhaps imperative for humans to, in a sense, accept autonomous AI systems. So, Roland, we'll go to you first, but I'd like to just hear if you can connect that back to whether your work is maybe a jumping off point for autonomous full defense systems. And we'll unfortunately have to keep the answers short. Thank you, Roland.
Yeah, so I think certainly automation is definitely needed for cyber defense in the future more and more. Whether it's only this fully automated AI, I think maybe in the long distance, yes. I think it still has a lot of problems, especially if you take it outside of the exercise environment that I was speaking of. If you see what Arthur was mentioning with the lack of transparency in many cases, of that people don't know what the AI is deciding and why. So I would, for quite some time, I would expect not the full trust in these AI-only approaches. And but in the long run, I think we are moving towards more and more automation, can be seen at some point as only AI.
Very much agreed also from my side, but maybe that becomes a good connection back to Arthur, if we can, in the short time remaining, just briefly, if you could say something about, whether you always see a human in the loop for this, or self-retraining and self-monitoring is part of the future.
So the question is, what follows explainable AI? Because I think maybe something will follow, something better. At the moment, it does not work without experts. Things change, inputs change, and I see automation in this type of research, and this automation is completely not transparent. So if there are training sets with hundreds of thousands of devices or hundreds of thousands with rules, then this is obviously made by some kind of automation. And this automation is not clear. So expert is always important. And regarding the only way to defend that is AI or machine learning, in my research context, it is a matter of time before adversaries will use device classification to find compromisable devices. So we, as researchers, have to use it quicker and remediate these devices. This is kind of the problem.
Indeed. Thanks very much, Arthur. And I regret that we have to end the session there. It's such a pleasure starting a discussion like this, and I think we'll hear more about that. Before I close off briefly, I'd like to very quickly mention that we'll have a 20-minute break now, after which, at 17 hours 20 Tallinn time, you may join the discussion on the stage one, and that's going to be the EU challenges and outlook for cybersecurity in the digital decade. So please join us there. In closing, I would like to thank you, the audience, everyone listening, and of course you, Arthur and Roland, for your excellent work and presentations, and of course the discussion. And I look forward to hearing from you next time. Thank you.